Okay. Yep. Thanks for pointing that up. This could be good for people to have later on. Thanks, Yannick. Okay. So yeah, as I was saying, we have these canonical commutative C-star algebra examples. Okay, and then one of the first really fundamental result in C-star algebra's theory was due to Gelfand. And his result says that every commutative C-star algebra is in fact of this form, that this completely exhausts all possible commutative C-star algebras you could ask for. And moreover, it's a nice correspondence, right? The X here, the space, is also unique, as long as you restrict yourself to locally compact Hausdorff spaces. So all the possible information you might like in your C-star algebra is really already contained in this unique, locally compact Hausdorff space. Another very natural example of a C-star algebra, a finite dimensional C-star algebra even, is what you get from looking at n by n complex valued matrices, right? And these again, I'm sure Karen must have mentioned this at some point, that these again form a C-star algebra. So in this case, again, you add entry-wise, right? This is the usual matrix sum. And the product in this case is now the matrix product, right? You don't do it point-wise, you actually use the usual matrix multiplication. And conjugation, the star in this case is just the conjugate transpose matrix. Yeah, and the norm in this case, again, important to point out what norm we're talking about. We're talking about the operator norm. So when you look at n by n matrices as if they are actually linear operators on an n-dimensional complex vector space, and you look at that vector space as if it's a Hilbert space, you look at the usual inner product, then the operator norm as a matrix, as an operator on that space, that's exactly the norm you need to turn it into a C-star algebra. And again, I'm not sure if Karen mentioned this explicitly, but this is another, I guess, fundamental result. And that is, in fact, this is pretty much all your finite dimensional C-star algebras. It's not quite, because you can also take direct sums of matrix algebras. These are again going to be definitely finite dimensional C-star algebras. But as if you look at all the possible direct sums, then in fact this exhausts the class of all finite dimensional C-star algebras. And again, you have this unique result that the n's here, the size of your matrices that appear in this direct sum, are in fact unique, up to ordering, of course, right? It doesn't matter if you switch around the order of these matrices. That doesn't change the isomorphism class, but these n's, modulo the order, modulo multiplicity, I guess, as well, this is unique. So this really goes back to, I guess, is Wedderburn. So Wedderburn was working in 1908, so this is well before anyone was talking about C-star algebras, but he had this result in ring theory, saying that every semi-simple, every finite dimensional semi-simple ring over the complex numbers, so algebra, I guess, over the complex numbers, has to be of this form. And C-star algebras are always semi-simple, so this gives you, as a corollary, this result can also be applied to C-star algebra. So that's great. We have a very good picture of what commutative C-star algebras are. These are just functions on spaces. We have a good idea of what finite dimensional C-star algebras are. These are just direct sums of matrix algebras. What about the remainder? What about infinite dimensional non-commutative C-star algebras? Well, here again, we have a canonical kind of example where you take a Hilbert space now, could be infinite dimensional Hilbert space, and you look at bounded linear operators, or equivalently continuous linear operators. And these form a C-star algebra. Again, summation is done, and again, in a sense, point-wise, right? Like the sum of two operators is the sum of their values at every particular point. The product now is composition. So the product of two operators is the value you get by applying one operator and then applying the next, right? And again, it's the operator norm that is the key norm you need to actually get you a C-star algebra. And the star is the usual adjoint, right? You have an operator on a bounded linear operator on a Hilbert space, always has an adjoint, and that gives you your star. And again, there's a theorem which says, in some sense, these are the only C-star algebras, even non-commutative, even infinite dimensional C-star algebras. So it's not quite, again, it's not quite saying that B of H itself exhausts this class, but rather closed star sub-algebras of B of H, C-star subalgebras of B of H, right? So you can always take any collection of operators, look at the closed star subalgebra they generate, and they inherit, you know, the same, the product, the sum, the norm, everything, and they will again form a C-star algebra. So it has to be closed, right? Because C-star algebras have to be complete with respect to the norm topology. The only issue here is that this theorem is, well, I mean, it gives you a very good picture, I guess, of what is going on, where these C-star algebras come from, but it's not quite as good as the previous two results we had, right? So the results of Gelfand and Wedderburn. So one issue you see immediately is that H is not unique, right? One C-star algebra can have many different kinds of representations on many different Hilbert spaces. I mean, Hilbert spaces are more or less all the same up to their dimension, right? But you can take direct sums of representations to get representations on arbitrarily large Hilbert spaces, right? And even for representations on the same Hilbert space, there are certain features that some representations may have, some may not. So there's no uniqueness here, right? And indeed, the Hilbert space itself, on its own, really tells you almost nothing about the C-star algebra, you know, that you get, the subalgebra of operators that you have. About the only thing I can really think of is that the size of your Hilbert space does, to a certain extent, bound the size of your C-star algebra. So if you have a separable Hilbert space, for example, then B of H, and hence any C-star subalgebra of B of H, will have to have size at most continuum, basically. But that's still pretty big. It doesn't really doesn't even have to be separable. Separability of H does not transfer to B of H. That's a very important thing to know. So yeah, it really doesn't help you so much there. It's a very nice theorem, of course, very useful, and you can. It's nice to know whenever you're dealing with C-star algebras, you can always pretend, if you like, that they're formed from actual concrete operators in a Hilbert space, right? When you're doing calculations and stuff. However, it doesn't give you such a great picture necessarily of the C-star algebra you're dealing with. But it does at least suggest one potential way of building interesting C-star algebras. And that is to start with your Hilbert space, start with some collection of operators on that Hilbert space, and simply look at all the closed SAS subalgebra they generate. So officially, this is the smallest C-star subalgebra of B of H containing those operators. Or put another way, if you want to, that's sort of a top-down approach, I guess. If you want to go from the bottom up, what you really do is you look at all sums or linear combinations of polynomials of those particular generators, and then just take the closure to get the closed star subalgebra that they generate. So in particular, you can do this when you're looking at groups, even finite groups. So how do we define the C-star algebra of a finite group? Well, firstly, I should point out that, yeah, here I'm roughly following some very nice notes of Ian Putnam. So I've got the website there in case you're interested. I'll do things in a maybe slightly different way, but these are very, very good notes if you want more details on the kind of things I've been talking about, I will be talking about today. So firstly, let's say we have our group G. In fact, at this point, it can even just be any set. And let's look at all functions from G to C, like just arbitrary functions, right? So there's no topology on G, certainly not at the moment. And so we're not worried about continuous functions or anything like that. Just all functions from G to complex numbers. And we're going to denote it by this little C superscript G here. So there's a standard way of turning this into a Hilbert space by defining a certain inner product. So I'm not sure, I can't remember the convention Karen was using, but my inner products will generally be conjugate linear in the first coordinate and linear in the second. So the way to define inner product in this case is just like so. You just look at the products of the individual values at each G, right? Except you take the conjugate in the first coordinate, and then just sum them all up. And you can quite easily verify that this is a sesquilinear form, as they often say, right? So it's linear in the second coordinate, linear in the first. Okay, so it makes it a Hilbert space. You don't have to, so Hilbert spaces also have to be complete, but because at the moment, we're saying that G is finite, right? Next lecture, or at least the lecture after that, we'll look at infinite groups, but at the moment, everything is finite. So completeness here is basically automatic. Every finite dimensional normed space is automatically going to be complete. Okay, so it's a Hilbert space with respect to pointwise sums, right? Just sum at each coordinate, just like we usually do, and likewise scalar products are just done coordinate wise. And now, if G is a group, we can look at some extra structure we get. So if G is a group, then there's a very natural way of associating an operator to every single element of your group. So what you do is you say, I'm going to define this operator, let's call it G hat, which is going to be a bounded operator on this Hilbert space, CG. So you just say that G hat operates on A and turns it into a new function. The value of this new function here at H is simply going to be the value of the old function A, but not at H, but rather now at G inverse H. So if you're, it's basically the shift operator. If your group G was Z, even though that's infinite, then G inverse here would just be H minus G, right? So you'd just be shifting your function on Z in this case, left or right by whatever number of coordinates G is, right? In this case, of course, we have finite groups, so this is not exactly what you're doing, but it's basically a shift permutation, I guess, right? You have your function, and then you've got a new function which takes all the same values, just at different points of your group. Okay. And now we have, well, these are all operators. And again, because everything is finite dimensional, we don't have to worry about whether it's bounded, right? It's automatically bounded. Okay, it's a linear operator. All linear operators on finite dimensional norm spaces are going to be bounded, so that's great. And so we can just now look at the star subalgebra or the closed star subalgebra, same, generated by all these operators associated to all these elements of your group. Yeah, and this is, I think this is what I was saying, right? So G is finite, so CGs and hence BCG, these are also finite dimensional, and so this is going to be closed. So it really is a C star subalgebra of BC of G. You might be tempted to guess or wonder at this point whether it's the whole of this, and we will see later on that, in fact, it's almost never the entirety of this. It really is a proper C star subalgebra of BCG. Okay, so what do we want to do? So we want to, well, first thing we want to verify is that the product of two operators, right? These operators corresponding to F and G, let's say, if you look at the corresponding operator, that this really is the composition of the operators corresponding to F and G. So the way we do that is we just do a little calculation. So let's look at the operator associated to the element, the single element, FG, right? So, well, this applying, if we want to know what FG is at some element of our Hilbert space A, which is just, remember, functions on our group, then we have to look at its value at various elements. So let's look at its value at a particular element H. So then we apply the rule, which says that, okay, this A of H is actually equal to A, but now not of H, but rather FG inverse H. And elementary group theory, we know this is just G inverse, F inverse H. And then we can take the G and the F out one by one. So this is really, remember, G inverse something is really the same as saying G hat operated on A of that same something, in this case, F inverse H. And likewise, you can now take the F out the front. So you find that this is really G hat applied to A, and then you apply F hat and you look at the value at H. Gives you exactly the same thing. So this is true for all H, right? So that tells you as functions, this F hat G A is the same as F hat G hat A, where the product here that I've sort of omitted, this is really just composition, right? Composition of operators, which is the usual product we use when looking at operators on a Hilbert space. Okay, great. So it really is a representation of this group. The product in the group really does correspond to composition of the operators that you're getting. That's nice. What about if we look at, say, next thing we want to show really is the adjoint of this operator really corresponds to the same operator, but this time the one you get from G inverse, right? And again, it's just a matter of doing a few little calculations. So let's look at the function, you have two, okay, let's start with A and B, which are just functions on your group, right? So we want to look at the inner product of A and B, in fact, not of A and B, but rather G hat operated on A with B. So we do a few expansions here. So remember, the inner product is defined by taking sums over all elements of G, right? Where you look at the conjugate of the value in the first coordinate and the value of the and then the value times the value of the second coordinate B here. And so you take the sum over all of H of G, right? But again, applying this rule where we just G hat A is by definition equal to A of G inverse H. And then just reorganizing things, noting that really what you're doing here, if you're taking the sum over all H and G, then in fact, this is exactly the same as if you're taking the sum over all K's and J's, but only those where J, K inverse happens to be equal to G, right? Because it's G inverse H, H, right? If you look at, let's see, J, K. So yeah, if you look at H times G inverse H inverse, right, in brackets, well then it'd be nice if I could write this down, but it would be H times H inverse times G. So the H and the H inverse cancel out and you're left with G, right? So it's really just rearranging the indices, right? You can maybe do a little bit of working here just to verify to yourself that this is again true. And you could do the same calculation, but this time with the operator corresponding to G inverse acting on B now. So again, just by definition, you take sums over all the H's in G of these two terms here. But G inverse hat B is by definition just B of G of H. And then again, noticing that if you take this second coordinate here, this G of H, multiplied by the inverse of this coordinate over here. No, is this right? Hang on. Yeah, the inverse of this coordinate over here, then again you get G. So just rearranging the sum, just taking the sum in a slightly different order, then this is really what you get. So exactly, these two things are exactly the same. Okay, so what does this all tell you? Well, this tells you that this G inverse hat here is the adjoint of G hat. Right? Remember, when you're looking at operators in a Hilbert space, the adjoint of an operator is the unique operator defined by saying I can either take that operator of A and then an inner product with B, or I can take the adjoint operator on B and then the inner product with A. So this uniquely defines this adjoint operator for any operator on a Hilbert space. So that gives you the first inequality. The first equality, I should say. The second equality is really just following from this previous fact. Remember that GH hat is the same thing as G hat, H hat. So in particular, GG inverse hat, which is just the identity of your group, hat, which is just the identity operator, that this is exactly the same as G hat, G inverse hat, right? So that's that part. So, and remember, again, when you're looking at operators on a Hilbert space, if the adjoint is equal to the inverse, then this is precisely what defines a unitary operator. So it's an operator which basically whose the operator and the inverse preserve all the relevant structure. They preserve the inner product. They preserve and hence they preserve the norm. So they're isometries, and also the inverse is also an isometry. This is basically a unitary operator. And now so this gives us a better idea of what products in G correspond to as in terms of operators, and what the inverse in G corresponds to the adjoint in the operator sense, right? Then what this also tells you is that in fact, all these operators you have, they're already closed under composition. They're already closed under the adjoint, right? The only thing they're not closed under is addition. Right? So the star subalgebra, usually you would have to take products and adjoints and sums, etc. But now we know we really only have to take sums and scalar products as well, I should say. So the star subalgebra generated by this is really just its linear span now. You only have to take the span of all these operators defined by elements of G. So that gives us a much, I guess, nicer handle on what this C star subalgebra really is. Now, what about, okay, so representing functions on the group. So there are some very special functions in this set here of all functions from G to C. These are these delta functions, which are just 1 at a single element and 0 everywhere else. So you'll note immediately that these, of course, span the entire subspace, the entire vector space here of functions from G to C. Everything can be written uniquely as a linear combination of these delta G's right here. And now we get a sort of nice simple observation by looking at how these operators G hat act on these delta functions here at some other H. Right? So again, it's just some nice simple calculations. So you want to know what this function is at some value, let's say F. Well, by definition, what we do is we first look at the F times the inverse of G and look at the value of delta H at that particular element. Okay, but what is this really? Well, this is going to be 1 whenever G inverse F is equal to H and 0 elsewhere. Okay, but to say that G inverse F is equal to H, well, this is exactly the same that F is equal to GH. So put another way, this is exactly the same as the value of delta GH at F. Okay. And this gives you a nice way of, I guess, taking the G through the delta, right? Like, so G hat operated on delta H is always just the delta function at GH. Okay, so now this naturally leads us to think about, well, what if we have this representation of our group, right? Each individual group element defines in a very natural way a kind of shift operator on the functions from G to C. Well, we can also define operators now, not just for group elements, but even for functions now from G to C, right? Before we were thinking of C to G just as a vector space, as a Hilbert space. But now we're kind of moving towards thinking of this CG as also being an algebra in a certain sense. So what I mean is that for every single function now, we can look at this natural linear combination of all the corresponding operators, right? So A hat we're going to define now to be the linear combination of the G hats, where the scalars involved here are precisely the values of A at each G. So what happens now if we look at, say, this A hat, this new operator we've defined for some function A at the delta function at the identity E of our group? Well, again, it's just a matter of applying the definition. So we can expand this A hat really as the linear combination AG hat for all G, right? Taking the sum over all G. But we just showed, remember, that G hat operated on a delta function really is just basically taking the G through, and G times the identity is just G. So this just gives you, in fact, the linear combination of these delta functions with exactly the same coefficients. So if you like, we are recovering the function A from this operator we've just defined, this A hat. So yeah, so what it really tells you is that exactly this, you can recover the function A from A hat. So you might think at this point that two different functions, A and B, that when you turn them into operators in this way, that perhaps they could give exactly the same operator, even if they were different functions. But this says that no, you can actually recover the function itself just by looking at the value of the operator at the delta function of E. So in particular, this is really an injective map. And it's pretty easy to see that this is also linear, where in the usual way you take sums of functions pointwise, right? And you apply scalar products pointwise, etc. And that in fact it ejects onto CG. It gives you the entirety of CG. Because remember, we already did a few elementary calculations and we showed that C star of G is not just the star subalgebra generated by these G hats, that actually it suffices just to look at linear combinations. It's the linear span of these G hats. And so if this map here, it includes all the G hats, and yet it also includes their linear combinations. Okay, well, therefore it must include the entirety of C star G. So it's a linear isomorphism from CG onto C star G. it essentially tells you that that now, even though we were first looking at operators, these G hats, we looked at the star subalgebra they generate, etc. That at this point we find out we've really just got a different way of looking at CG, this thing we started with, not as a Hilbert space now, but in a different way we can look at it as a kind of C star algebra. Okay, but to really justify that claim, we have to work out what the operator product in here, right? Just the usual operator composition here. What does that really amount to then when we look at the corresponding elements of CG here, right? If we can't describe operator composition, well, then we can't really do much with the functions. We really would like to see operator composition as some kind of simple operation in terms of the functions. So let's do this. Take some functions, some complex value functions on our group G. Let's look at their operator composition, right? A hat composed with B hat. We know that this map from A to A hat is surjective. So therefore it must be of the form C hat for some possibly different function C, right? But we also know how to recover the function from the operator. We just look at the value of the operator at the delta function at E. Right? And we also know that when you have B hat and you operate on delta E, this is really just going to give you back B. So we're already pretty close. We already know that this C here has to be exactly the value of A hat operated on B as just a function. And now do some nice elementary calculations. So what is A hat B at some particular value G, let's say? Well, A hat B is by definition the linear combination of all these AH hat things applied to B. And then we're looking still, remember, at a particular value G. Okay, but these H hat B's, again, by definition, this is just what you get by taking the H through, but actually making it H inverse. We're looking at the value of B now at H inverse G, and still taking the sums over all those H's in G's. H's in G, I should say. Okay, but again, it's just a sort of little trickery. You can rearrange these terms and do the sum in a slightly different way. And really, you'll notice the product of H and H inverse G here is always G for every single value of H. So equivalently, what you're really doing is you're looking at this new function you get, let's call it AB, let's call it the convolution of A and B. It's the new function you get by saying A, B at G is just a product of all those values in A and B at particular elements of your group, which always have the same product. This is, I think, the best way of visualizing it. So that when we take operator composition, this is exactly the same as taking the convolution and looking at the corresponding operator. And it's also the same as taking just the corresponding operator of A and operating on B. That all of these things are really just the same. They're really just two different instances of convolution. So we don't, even though at first these seemed like they were somehow different, right? That there's a difference between taking the composition of two operators and definitely taking the value of an operator at some particular element of our Hilbert space. When you associate all the functions in the right way, really these are just two separate instances of convolution, this convolution product. So now we're starting to get somewhere. What about adjoints? If we look at adjoints of the operators in C star G, but then translate that in terms of functions from G to C, what do we get? Do we again get something we can maybe describe? So let's look at the adjoint of A hat. So again, we know this is equal to B hat for some B. It's just a matter of finding out what that B is. And to find out what the B is, we simply look at its value when we operate on the delta function at E. So again, just do some calculations. So the adjoint at A, what is this really? Well, it's really just the adjoint of the linear combination of all those operators. So you can really take the adjoints individually of all these G hats multiplied by the scalar AG. And adjoints, remember, are conjugate linear. So it's really the conjugate of AG, not just AG itself. And we already worked out before that G hat on its own star, that adjoint is exactly the same operator you get from G inverse now, G inverse hat. And that when you operate on delta E of anything hat, well, again, it's just taking it through. So it's really just delta G inverse now. So this tells you essentially what's going on, right? That if you look at the function you get, which corresponds to this adjoint operator here, then really what it's doing to the function A here is it's saying that the value at H is no longer the value at H, it's the value at H inverse followed by the conjugation operation. Right, so A hat star is the same as A star hat, where by definition we set A star of G equal to the conjugate of A at G inverse. So again, we're just translating all these different things. We're translating operator composition, we're translating adjoints in terms of more, I don't know, explicit functions, if you like, explicit operations on the functions, which you can view as defining your C-star algebra. What about inner products? Well, again, inner products are essentially coming from the convolution product. All these different kinds of products we had running around are really just different kinds of instances of convolution. So remember, we defined the convolution product of A and B here to be the sum of AG conjugate BG for all, summed over all G's. Okay, but we can rewrite this conjugate now really as A star G inverse, right, where A star is what we just had on the previous page. Okay, again, notice that G inverse G, just always the product there is just the additive, the identity of your group E. So really when you say taking the sum over all G, you're really taking the sum over all possible products of J's and K's, which give you the additive inverse E. So just the inverse of your group E, sorry. Okay, but again, look at this. This is looking rather more familiar. This is exactly convolution. This is exactly the convolution of A star B at the particular value E. So it's again turning even the inner product can be written in terms of convolution. Basically, it's convolution at a particular value at this point. So just to recap, at the very beginning, we looked at this functions from G to C as a Hilbert space. A Hilbert space with a 2 norm coming from this inner product. So the 2 norm of any element A is just equal to the square root of A inner product with itself, which in this case is just the convolution of A star and A at the value E. On the other hand, we eventually found out that CG can also be identified with C star of G. And under this identification, your C-star algebra norm, the operator norm in this case, is really coming from looking at the convolution product. Right? So the operator norm of A is by definition, the maximum, the supremum of all the possible values of A at all possible values of your Hilbert space over the norm of that element in the Hilbert space, which is just the 2 norm. But we know that products correspond to just convolution products. That's what this AB is. So this is really just another way of saying that. Right? So instead of trying to, I don't know, imagine that we're really looking with operators, it's just really we're looking at functions from G, pardon me, from G to C in 2 different ways. And I thought it'd be interesting at this point to see what is really so special about these norms, or the B norm in particular, because there are a lot of other different norms you could put on functions from G to C. Right? There's probably a lot of other norms that you would probably think of more naturally, like, for example, the infinity norm. So if you were dealing with continuous functions, right, this is the supremum norm that we're really used to. So what if you were to look at C of G now, but instead of looking at the 2 norm or the B norm, we looked at the infinity norm? Could this also give us some kind of C-star algebra structure maybe? And it turns out the answer is definitely not. I mean, it satisfies one nice property you would expect. So the infinity norm of A star is definitely the same as the infinity norm of A, right? Because this A star, remember, is just going to be the conjugate of your values of A, just at slightly different points of your group. However, this submultiplicativity, this fails. So it's not even going to define a Banach algebra norm, and definitely not a C-star algebra norm. If you want a nice simple example, well, you don't have to look further than the group with two elements, right? So an identity and some non-identity whose square is the identity. And just think of the function, let's say A, which is 1 at both G and E. Well, then its infinity norm is certainly 1. But if you look at the square, right, the square with respect to convolution, well, then you'll notice that A squared at any value, let's say the identity to start with, this is going to be the sum of the values G, and the sum of the values at E and E, right? These are the only two ways you can multiply two different elements to get the identity. So this is 2, and likewise at G, it's also going to give you back the value 2. So it goes from being 1 everywhere to 2 everywhere, which is not what you wanted, right? 2 is not 2 is not below 1 squared. So this tells you this is not a Banach algebra norm. Okay, so that is somewhat reassuring. This is why the infinity norm didn't work, right? It would work if we were doing just point-wise products, right? This is exactly what Gelfand really was saying, right? But because we are defining this very different kind of convolution product, it's not going to be submultiplicative with respect to that. That's why we have to look at a different kind of norm. A slightly better norm, which is indeed very useful in certain circumstances, if you know about harmonic analysis, then you'll find that the one norm is used quite a bit. So this is a much better candidate. So here what you do is you look at all the, you don't look at the supremum, you look at the sum of all the absolute values of these, of your function A at every single G. So again, it's easy to verify that, taking sums of elements or taking sums of their conjugates gives you exactly the same. So the norm of A star in the one norm is exactly the same as the one norm of A. And also now we do in fact get submultiplicativity. And this is a fairly simple exercise, right? Because you notice that, so taking all the sums, which this is equal to this if you expand the definitions, and we know that the modulus function itself is subadditive and submultiplicative, in fact even multiplicative. So this gives you this inequality here. So there you go, you've shown that the one norm is submultiplicativity. So what might fail, you might ask? Well, why weren't we using the one norm to begin with? Or were we using the one norm? Is this the same as the operator norm? But no. So it's a Banach star algebra, but here you see clearly why this extra C star condition is so important. This is the only property really that fails. So A star A, the one norm of that may be different to the one norm of A squared. And remember, this is the key defining property of a C star algebra. So the actual calculations might get a bit messy, but I mean, it's a fairly elementary kind of example once you know what you're doing. So instead of looking at the 2-element group, let's look at a 3-element group. And let's look at a function which is, say, -1 at the identity, but 1 at the other 2 elements. So let's look at this function A. Well, A is equal to A star. That's not too hard to see, right? That just switches the G and the G squared, but these are the same value. And now look at the square of A, the convolution of A with itself. So if you do this at E, you'll find that in fact what you end up with is just 3, so it's just 1 plus 1 plus 1. But the problem is that G and G squared, you get a bit of cancellation happening, right? So if you look at AG, well, it's -1, right? 1 times -1. But on the other hand, if you look at AG squared, well, the -1 gives you a positive one. And likewise with A squared at G squared. So that you again get a couple of these cancelling out and you're left with -1, -1. So taking all the sums, 3 plus 1 plus 5, 1 equals 5, which is definitely not the same as 3 squared. So this is where things fail. Okay, so let's get back to looking at the actual C star of G. So there are a couple of elementary observations we can make. First one is really regarding commutativity. So if you have a commutative group, and I'm usually called an abelian group, right, where all the group elements commute, well then it's not too hard to see that the corresponding operators also commute, because by definition the or not by definition, I guess, we worked it out that the operator product in C star of G is exactly the same, corresponds exactly to the product within G itself. And if these operators all commute with each other in the usual composition, then of course their linear combinations will also commute. So the whole thing, the whole star subalgebra, the whole C star subalgebra that they generate will also be commutative. On the other hand, this really is an if and only if. And to see why, we'll just recall this fact that this mapping from G to G hat is injective. Right? We showed that it was even injective on functions from G to C, but it's certainly injective on G itself. Right? So if G is not commutative, then we're going to have at least two individual elements such that GH is not equal to HG. And again, composition corresponds to the product within G itself. So if GH is not equal to HG and this map to hats here is injective, well then these two things are not equal. So the two operators do not commute. So it's a simple observation, but also quite important, and that is that the finite group G is commutative if and only if the corresponding C star algebra is also commutative. So let's take another look at this. This cyclic group, or the only group really of order 3. So if we look at this C star algebra, C star of G, we know that's also commutative. So we can use either the Gelfand theorem or the Wedderburn theorem to deduce that in fact the C star algebra we have is really just 3 copies of C direct summed together. Right? So as a C star algebra, it's perhaps not so interesting, but it's interesting to see, I think, what the elements of G correspond to within here. Your first instinct might be to say that, oh, okay, maybe each element of G corresponds to 1, 0, 0, or 0, 1, 0, and 0, 0, 1. Maybe those are the 3 elements here that they should correspond to. But a moment's thought will reveal that that can't be true, because if you look at the element 1, 0, 0, and you look at its square, let's say, well, then again, you get 1, 0, 0. But we know that this G here, that's the only idempotent in this group is the identity itself. So that can't be it, right? So what do the individual G's correspond to within this algebra? Well, if we look at the operator coming from the identity element of your group, we see that really is the identity operator in the on the Hilbert space as well, right? Okay, so the identity element of your C star algebra, I should say. Whenever you multiply any element, it really doesn't change it. Okay, so we know that E hat at least has to be the units of C star G. Units are unique. And so what that tells us is that E hat at least wasn't 1, 0, 0, it was really 1, 1, 1. Right? So that's a good start. What else do we know? Well, if you take G hat cubed, same as G cubed hat, which is the same as E hat, right? So that tells us that each of the individual coordinates corresponding to G hat must be cube roots of 1. Right? Okay, so if that's the case, what could they be? You might think, okay, could 2 of those cube roots be the same? Could we have x equal to y or y equal to z? Could they be the same cube root, for example? And then you see the answer is no, because, well, if that were true, then once you take the square, let's say, then an x and y were the same, then taking the square, x and y would still be the same, right? And so that would mean these 3 elements you get, E hat, G squared, G hat squared, they'd be linearly independent, right? They'd always be the same in the first 2 coordinates, say. And that contradicts the fact that this map here is supposed to be injective, right? It's supposed to be a linear isomorphism from some 3-dimensional space onto another 3-dimensional space. So that can't be it. So really this G hat must correspond to something of this form, like 1 z squared z. So it must be the 3 distinct roots of unity in the complex plane, or some permutation. The ordering here again does not matter. It could be z1, z squared, or whatever, but it has to be something of this form. Okay. So yeah, even something very simple, right? Like the cyclic group of order 3 has a perhaps slightly slightly unexpected representation when you look at it in terms of the Wedderburn or the Gelfand decomposition. And I think that it gives you a nice, at least a nice little picture of what's really going on. Okay, the nice thing about these finite group C-star algebras, like as C-star algebras, they're alone, they're perhaps not so interesting, because we already know what all finite dimensional C-star algebras look like. But what is interesting is the connections between the group structure and the resulting C-star algebra. So in particular, you can look at ideals. So one question you might immediately ask, which I kind of hinted at the very beginning, was could you take a finite group, look at the group C-star algebra, could that actually be just another way of looking at Mn, just n by n matrices, right? And again, the perhaps surprising thing slightly at first is that this is never possible, right? Except when n is equal to 1. The reason being that all these finite group C-star algebras have a very canonical one-dimensional ideal. Maybe if you're quick, you might even guess what that ideal is. Well, it's one-dimensional. What could be its generator? What you can do is you can look at the function A you get by just mapping every single element of your group to 1, let's say. And the claim is that in fact generates an ideal. That in fact, and to show that it generates an ideal, what you really have to show is that, well, part of what you have to show is that it really commutes with all these other elements. So let's look at what happens if you multiply on the right by one of these delta functions, delta g. So again, expanding the definitions, A delta g, what does that really mean? Well, so delta g, yeah, A of delta g is the same as H, is that A, HG inverse? Yeah, because we're taking the convolution product. So it has to be really A of HG inverse delta g of g. That's the only way you could get a non-zero product in your sum if you're looking at this in terms of convolution. Okay, so this is A HG inverse, and that, remember, we're setting it to 1 everywhere, so that's just equal to 1 as well, and likewise for delta g of A. So when you look at the product of A and delta g, you again get exactly what you started with. This is just A, right? So A and delta g commute, and in fact, they don't change A one little bit. And so in particular, you can do this with delta g's, but then the same essentially applies with linear combinations. Any linear combinations of the delta g's will again give you just some scalar multiple of A, the operator you started with. So if you look at all those scalar multiples, then you see that you in fact you can get an ideal. And certainly, if you look at the scalar multiples, it's certainly a linear subspace, but it shows it's also closed under composition, even with elements outside of C of A. So this is an ideal, very nice, and it's clearly one-dimensional, right? It's just generated by a single element as a linear subspace. Okay, and in the Wedderburn decomposition, what these ideals are, certainly the minimal ideals, these correspond precisely to those summands, right? Remember in the Wedderburn decomposition, you have like Mn plus Mn k, right? Like k many summands, and the individual identities on each of those summands, these are the ones that or I guess each one of those summands, I should say, is itself an ideal within the larger C-star algebra. It's a minimal ideal. So what this really means in terms of that picture, this Wedderburn decomposition, is that the C-star algebra of G in its Wedderburn decomposition has some C at the start, right? Or anywhere, I guess. The order doesn't matter. But the point is, one of those summands has to be just C itself, just the complex numbers, not any higher matrices of the complex numbers. Okay. And that was in terms of ideals or minimal ideals, but you can also start then thinking about the center, right? So notice that any central projection, in fact, in any C-star algebra now, like even infinite dimensional C-star algebra, naturally defines an ideal. So it's just it defines a corner. I think Karen was talking about corners, which in general are hereditary C-star subalgebras, and that works for any projection. But if it's central, then that corner will in fact be an ideal, right? Simply the ideal you get by taking all products with all elements of A. And in the particular case that A is finite dimensional, in fact, these are the only ideals. Basically, the reason being that, well, any ideal of finite dimensional C-star algebra is finite dimensional, and all finite dimensional C-star algebras have a unit. So the P in this case would just be the unit of that ideal. Okay, so a more general question, if you like, than the previous one would be to say, not are there any ideals, but what are the minimal projections? In fact, what are all the central elements? If we could describe all the central elements, then we would basically be getting a description of the ideals as well for free. Now, these are essentially determined by conjugacy classes of G, it turns out. So hopefully you know a bit of elementary group theory, and you know what the conjugacy relation is. So you say two elements of your group G, let's say F and G, are conjugates if I can find some further element H, such that conjugation of G by H, so H inverse GH, gives you F. So if your group is commutative, for example, then this trivializes, right? Because you can then just move H inverse over to the right and then cancel this out with H. So this is only really an interesting relation when you're dealing with non-commutative groups or non-abelian groups. If G here is the inverse, if G here is the identity, and again, you can cancel these out. So that tells you that even in a non-abelian group, there will always be a very simple conjugacy class of the identity consisting of a single element. And you can talk about conjugacy classes because these are just equivalence classes with respect to this conjugacy relation. Again, little exercise, you can show that it's this relation you get here is both reflexive, symmetric, and transitive. So it's like a partial order, except instead of anti-symmetry, you have symmetry. So, I mean, well, what would be can we do a quick verification? Let's see, what if G is equal to F, then is this trivially holding true? Let's see, like F, FH or HF, is that true? Okay, so in symmetry, yeah, symmetry is true because, well, if you multiply on both left and right by H inverse, if you multiply on the left by H and on the right by H inverse, then that shows you that G is in fact conjugate to F by this relation. And, well, transitivity, yeah, basically if you put another element there, then this would be conjugation by the product. I mean, anyway, I mean, you can verify this for yourself. It's not so hard. So because it's an equivalence relation, that means we can split up our group into equivalence classes. So each G determines a conjugacy class, the unique equivalence class containing that particular element. And they partition the entire group G. So why a conjugacy class is important here? Well, because, like I said, they really determine the center of your group. So let's take a conjugacy class and call it C. And let's define a delta function like we did before, but this time it's going to be one, not on a single element, but in fact on every single element of our conjugacy class, and zero outside. So the first observation is that as long as C is a conjugacy class, then this delta C, this function here, is indeed a central element, right, of your C-star algebra. To check this, again, it suffices to just look at the delta functions, right? If you can show that it commutes with all elements in something which generates your C-star algebra, then in fact, it has to commute with every element in the entire C-star algebra. So let's look at what happens if you look at the convolution product with delta G. And let's look at a particular element H. So so by definition, remember convolution, you're going to take sums of products where the two products have to have value H, right? But because this is a delta function, there's only one option for the second coordinate, right? That would give you something potentially non-zero. So all the other products in your sum are going to be zero. What you're going to be left with is delta GG and delta C of HG inverse, right? And this is one, so we can just forget about that. And so what we're left with is delta C HG inverse. And why is that true? Well, just think about it for a second. Delta C HG inverse will only be one when HG inverse itself is within C. That's what our definition up here was saying. But, well, multiplying on the right by G, this is precisely saying that, here's a typo, that H is in little g. See, this should be a little g here, right? In fact, it shouldn't be, well, it shouldn't be G, it should be C little g on the right-hand side, just like I've written here. So scratch that thing there and replace it with CG, right? Because you're multiplying on the right by G to cancel this guy out. Okay. So sorry about that. I knew a typo would slip in there eventually. Okay, so this gives you a very convenient way of working out what delta C delta G is, and likewise for delta G delta C, pretty much exactly the same kind of calculation. So then what happens if you look at the conjugation essentially? What if you look at delta G inverse C delta G? Well, we can take those inside now, and we see that this. Okay, so what do we know? We know that this is equal to this, and that because C is a conjugacy class, this is really just the same as C. Right? So what does that tell us? That tells us that, well, this operator, this composition of different operators really just gets you back to what you started with, which rewriting it, multiplying by delta G on the left-hand side here, tells you exactly that delta C commutes with delta G. Okay. And like I was saying at the start, this immediately then extends to, in fact, all elements in your C-star algebra because they're all generated by these delta G's. Okay, so that's one half of what we wanted to show, right? Conjugacy classes definitely give us central elements. The next question, though, is whether they in fact exhaust all the central elements. Okay, so let's say. So what we want to show is that the center is in fact spanned by these. Of course, it couldn't be just these alone because these aren't closed under taking sums and scalar products. But when you take sums and scalar products, this gives you the entirety of the center of CG. Okay, so way to do this is just take any central element. Okay, in particular, it commutes with these delta G's. But what does that mean? Well, it means, again, rewriting it, multiplying by delta G inverse on the right-hand side. We can rewrite it like this. Okay. But then you look at the value at some H and do all the necessary calculations. So right, this is convolution. So again, this is essentially a sum, right, over all those different products of different values of delta G inverse A and delta G. All of those products which give you H, but the problem is, again, almost all of those will be zero. The only possible non-zero option for the first part of your product is going to be the value of G inverse. The only option for the second or third, part of your product will be G here. And the only way to get all those three things to have product H is to look at the value here at A at G, H, G inverse. Okay, so this is one, you can cancel out one, you cancel out, and this is what you're left with. So putting that all together, what this is all saying is that A is constant on every single conjugacy class. And think about it for a second, that's really just saying you can write A as a linear combination of the elements which are 1 on each conjugacy class and 0 outside, all these delta C's for conjugacy classes C. Yeah, so we've nailed down the center, which is really nice. And another quick observation, but again important, is that the linear combination is unique, right? Because conjugacy classes are disjoint. So there's no way you could take some linear combination of these delta C's. There's no way they could cancel out, right? So this it basically gives you a way of working out the dimension, right, of your center here, right? So the dimension of the center is going to be exactly the number of distinct conjugacy classes of your group. So my sync is going a bit crazy there. Okay, so now we're sort of getting into some very basic representation theory of finite groups. So if we have some group, then we know that on the one hand, if we look at this Wedderburn decomposition, that the dimension of the center has to be exactly the number of summands here. So if we have k summands, well, then that means the dimension of the center is k. Even though we also know that the k has to then correspond to the conjugacy classes of G. We also know the total dimension of our C-star algebra has to be the sum of the dimensions of all those summands. So these are just, and each mn, right, has dimension n squared. Right? So the total dimension of your algebra, which we also know corresponds to the total number of elements of G, has to be just the sum of squares corresponding to the sizes of the individual summands in the Wedderburn decomposition. So we have in both cases, we have two different ways of calculating the dimension of the whole algebra and the dimension of the center. And sometimes this alone is actually already enough to tell you what the structure of your C-star algebra is for some particular group G. So for example, take the symmetric group on 4 elements. So these are just all possible permutations of a 4-element set. So the number of permutations there is going to be 24. So it's always going to be 4 factorial, right? And I haven't got them at hand, but I know I looked this up earlier, and that these have exactly 5 conjugacy classes. It's group S4. Okay, so in that case, what could be the possible Wedderburn decomposition? We know that there has to be 5 summands. Okay, but we also know that when I take the sums of the squares of these corresponding sizes, they have to add up to 24. And just playing around with sums and sums of squares, you'll see that there's really only one way of doing this, right? We also already know, I guess, one thing, that there has to be at least one in the summand in decomposition, and in this case there are 2. And the only way of getting these sums of squares to add up to 24 is in fact like so. So it seems somewhat random that a very standard group like S4, right, could have this decomposition where there's a couple of 1s, there's a couple of 3s, and there's 1, 2. I mean, it doesn't seem immediately obvious why that would be the case. And trying to do this explicitly, I think, by looking at, I guess, generators of the C-star algebra, you get might be somewhat tricky. But just from some elementary observations using these little results about conjugacy classes, etc., you can already work out exactly what the structure is. And lastly, I guess I might finish a little early today, but lastly, I wanted to talk about the canonical trace of a group C-star algebra. So there is always going to be a faithful tracial state. So a trace where the norm is 1 and where it's faithful in the sense that T A star A is 0 only when A itself is equal to 0. And it's given very simply by just looking at the value at the identity of your function A. Right? So we're again moving beyond this idea of C star G as operators, and we're looking at really convolution products on functions on G to C. So why? Well, we have to prove that it really is a trace. So let's look at this. What is the value of A star A, let's say, at E? So first thing, to show that it's a trace, we have to show that it's a state, or we have to show that it's a positive functional. So it has to take positive elements to positive elements of C. So let's look at A star A, which is a positive element in your C star algebra. Let's look at the value at E. And we see that, well, it's the sum over all these possible products where G and G inverse have to have value E. Okay, and that, remember, A star G inverse is really just the same as the conjugate of AG, the conjugate in terms of the complex numbers, not in terms of groups. Right? Okay, so this is just the modulus of AG squared. And that's positive, sums of positive are positive, so great. We know that this is indeed a positive element. Another simple calculation is to look at what happens at delta E, right? So delta E is the function which is 1 at E, 0 elsewhere. Well then, by definition, taking the value at E is definitely 1. So any positive linear functional which maps the identity of your C-star algebra to 1 is a state. Right? That tells you, in fact, that the norm of T as a linear operator has to be at most 1. And moreover, it's easy to see from this calculation here that T A star A is 0 only if A is equal to 0, right? If T A star A, if the value of A star A at E is 0, if this sum is 0, then as all these individual elements in the sum are positive, that means they would also all have to be 0 individually. Right? That tells you that your A would already have to be the 0 function. So this is exactly what tells you that tau is a faithful tracial state. Okay, so and last but not least, right, we've shown it's a state, we've shown it's a faithful state. We have to show it's actually a trace. And the key extra property of a trace, remember, is that the value at a product, AB, has to be exactly the same as the product, but in the reverse order, BA. And this is again some nice calculations. So look at the value of the convolution product of AB at the identity E. So it's this sum here, but you know, individually, these values here, these are just complex numbers. So of course I can just write this in the opposite order as B, G inverse G, but then I'm taking the sum over all elements of my group. So I could also take the sum over all inverses of elements of my group and just replace G with G inverse here. And then this is telling you exactly that, well, this is just by definition, the convolution product of BA at the identity of your group. So indeed, it's a trace. So great, we have a very simple, canonical, faithful tracial state on any group C-star algebra for a finite group. Okay, but what would that be for some particular kinds of examples? And so again, let's go to my favorite, very simple example of the 3-element group. So take your three-element group and let Z be just some particular, non-identity cube root of unity. So remember, we were working out the structure of the group C-star algebra here, and basically we got a correspondence with just the direct sum of 3 copies of the complexes, where the delta function at G, or G itself, G hat, it's exactly pretty much the same thing. This corresponds to a triple where you have 3 distinct cube roots of unity, right? And likewise, the square is the same, but then S squared and Z get reversed, and then the cube gives you the identity here. Okay, so what does the canonical trace here really look like in terms of 3 copies of C? Because there's many different functionals on this, right? You could look at just the projection onto one coordinate, right? That's definitely a positive linear functional. It's not that one. I think won't be faithful, right? Because it won't have this property that tau of A star A equals 0 implies A equals 0. But you could take linear combination. You could basically take linear combinations of any of those particular coordinates, those 3 coordinates, as long as the linear combination. You would again have alpha times the first coordinate plus beta times the second coordinate plus gamma times the third coordinate, right? And as long as alpha, beta, and gamma are all positive, and as long as they sum it to 1, then that will give you a faithful tracial state, right? So there's a lot of different options you could choose for your alpha, beta, gamma. And the question is, what is the canonical one here? What does that really correspond to in terms of 3 copies of complex numbers? Well, we claim it's probably the simplest one you could think of. It's where you take alpha, beta, gamma all to be 1/3. You take 1/3 of the individual coordinates and sum them up. And really, it's just a matter of checking on the generators that it gives you the right value. So we know that tau of delta E, the identity of our C-star algebra, that is 1, right? So what happens if we look at pi inverse? So what if we look at pi inverse of this tau? Well, this is, if we look at 1/3 of the individual coordinates, right, and we add them all up, we again get 1. So this is exactly what we wanted. On the other hand, if we look at like 1/3 of these, the sum of all these different cube roots of unity, well, then the 2 complex parts cancel out, and the real parts also cancel out with 1, right? So we end up with 0 in this case, which we know is exactly the same as tau of delta G, right? So tau is just the value at epsilon, but delta G is by definition going to be 0 at the identity. So this gives you 0. And likewise, again, if you add up the different cube roots of unity, but in a different order, well, that doesn't change the sum, right? It's still 0, and so this should be a g squared here. Sorry, not delta g squared. Okay, so this particular trace we have by looking at 1/3 of the coordinates summed together agrees on the generators with the canonical trace. So therefore, it must in fact be the canonical trace. Right? And you can do similar arguments even for larger n's, for larger cyclic groups. So that gives you a somewhat different way of looking at things. So yeah, that's pretty much all I prepared today. Maybe just at the end, I can sort of give you an idea of where we're going next. So this was all with finite groups, and of course, finite groups and finite groups on their own. I mean, finite dimensional C-star algebras we know are not so interesting. We already know what they are thanks to the Wedderburn decomposition. They give you some interesting connections between the sort of linear structure and the group structure to do with like conjugacy classes, etc. But really, in the end, this is a C-star algebra course. You would like to look at more. You'd like to create some interesting examples of infinite dimensional C-star algebras coming from groups. And to do that, of course, you need infinite groups. The only problem with infinite groups is in defining some of the things at the start. So the problem is you have these sums defining convolution, let's say. And if you're dealing with infinite groups and functions on those infinite groups, it's not always clear that these sums will converge. And so then you have to work out what norm you're talking about, and then actually say, well, the sums have to converge in this particular norm, or alternatively, you look at operators and say, well, I have some star subalgebra of operators, and then I take the closure of those operators, right? Which may no longer be the same as the star subalgebra you started with. And there are various complications about whether different norms you could use, so you end up with this reduced C-star algebra corresponding to a group, which could be slightly different to or very different, in fact, to the maximal group C-star algebra. There are exotic things in between, although I don't think we will talk about them. But yeah, just to give you a flavor of what was really going on without having to worry about completion and different possible norms you could be using, I thought it was best to first go for the finite case. And in fact, I think next lecture I would like to talk about as well Untitled groupoids. So that was the other thing we wanted to move. It turns out that it's actually important to be able to generalize from groups to groupoids to be able to get really interesting examples of C-star algebras. Even for finite groupoids, you can kind of see this already, because remember when we went back, we found out that there were certain finite dimensional C-star algebras which we could never get from any group, right? We could never get Mn, right, for any n greater than 1. However, if we generalize slightly from finite groups to finite groupoids, then you find there is a very easy way of getting even these kinds of C-star algebras Mn. There's a very canonical finite groupoid you can associate to any finite dimensional C-star algebra, and the C-star algebra of that groupoid will give you exactly what you want, right? And then the extra stage is to look at Untitled groupoids, to give these groupoids a nice topology. And that will allow you to also look at even the original, commutative C-star algebras that Gelfand was looking at, and look at them in terms of as a groupoid C-star algebra, of an Untitled groupoid with a very trivial groupoid structure, but with a non-trivial topological structure. So combining all these things, and then I'm not sure if I'll get to it, but then you might even like to go further and look at certain Fell bundles. So where you look at Untitled groupoids, but you look at bundles of C-star algebras or bundles of certainly subspaces and combining them in an appropriate way to get a C-star algebra. That sort of gives you the most general combinatorial way of defining C-star algebras. But that's just sort of a taste of what is to come. So yeah, thank you all for coming, and I hope to see you all. Oh, are there any questions first? Yes, I can see something in the chat. Okay, does the proposition C star G commutative infinite G also hold for locally compact infinite groups? So yeah, we we won't talk about topological groups so much. We'll talk about Étale groupoids, but Étale groupoids, for a group to be Étale, it in fact has to be discrete. So we won't worry about that so much. But for infinite discrete groups, definitely, yes. I'm pretty sure G is commutative if and only if C star G is commutative. For locally compact groups where you're also looking at convolution with respect to like a Haar measure, and then I think it should also be true. Yeah, I'm not 100% sure because I don't deal much with locally compact groups so much, but there are certainly people who do, and I would be very surprised if you could somehow have a non-commutative locally compact group which gave you a commutative C star algebra. But yeah, but don't quote me on that. This is not my area. Yeah. Does that answer your question, Yannick? Yep. Okay. Good. Any other questions? It doesn't.
What about? Yeah.
Yep. You have a question?
What about twists of group multiplication? For example, if I have some cocycle and I want to twist the group multiplication, am I right that you will get a new C star algebra only if your cocycle is not coboundary? So it's a non-trivial cohomology.
Yeah, I would guess so. But yeah, but this is a very good question. So yeah, there's another thing you can do to generalize these examples. You can look at these twists on the groups. You could maybe, yeah, in fact, this theorem I had before actually, where you only get, you will never get like Mn. I'm not 100% sure that you wouldn't get Mn. You might be able to get it by twisting your group in an appropriate way. I'm not totally sure. But maybe not, because like this, surely this example should also work even for the twisted case when you twist with a cocycle. Right?
Yes.
Yeah. Okay. So this should be fun.
You will still have get a group multiplication by twisting cocycles.
Okay. So it's not clear that So you won't get all possible finite dimensional C star algebras, although you could conceivably get some that are not obtained without a twist. I'm not sure, but yeah, you're looking confused there, but I'm not totally sure about that. But definitely this is something to look at. And in fact, my general, I mentioned just at the end there that we might talk about Fell bundles over Étale groupoids, and when you have a twist, that still gives you a very natural way of looking at a bundle over your group or groupoid. So once you move to the bundle picture, then you're already in a sense including twists as well. But yeah, these are certainly important examples. And there are various interesting examples, like with Étale groupoids. There's a very nice characterization of when you get a simple C star algebra out of them. However, I think the corresponding result for twisted Étale groupoids is not quite so clear, I think. So if you're doing Fell bundles, it's not quite as obvious. But yeah, there are definitely interesting questions about what happens when you suddenly introduce a twist, a non-trivial cocycle.
Okay, thanks.
Okay. Yep. No other questions. Okay. Well, in that case, we'll end today's lecture. But thank you all for coming, and hopefully see you all next week.